Because of the implication.
Oh, okay. You had me going there for the first part. The second half kind of threw me.
All right, now it's time to learn about the implication. In English, we often say things, that have the formula, if this, then that, right? Fairly common. If we say things in that format, we can take these segments of the sentence and assign them to logical statements. So we can call this one P and call this one Q. And in that case, we say P implies Q, right? P implies Q. We usually use the double line arrow simply because, remember, we use the single line arrow to indicate a function, right? So we usually use the double line arrow, but that means if P is true, then Q is true. That's it. That's all an implication is. How about if we have the sentence, if it's raining, the sidewalk's wet. So if R, it's raining, that implies that the sidewalk is wet. Make sense? So this is all kind of intuitive. Oh, wait, one more thing. What about if the start of the implication is false? What if it's not raining, right? What does that say about the sidewalk? Well, the sidewalk could be dry. The sidewalk could still be wet. We don't know. So we always assume that the implication is true if the left-hand side is false, right? And let me go into the definition, and then we'll draw this up in a truth table, all right? Okay, so according to your book, we define P implies Q to be the Boolean function called implication, or P implies Q, or the conditional of Q by P. As a Boolean function, P implies Q has the following truth table, right? Remember, if P is 0, then it doesn't say anything about P implies Q, so we assume that to be true. If P is 1 and Q is 0, well, that means that P does not imply Q, right? So we're going to call that one false. But if P is 1 and Q is 1, that means the truth of P implied the truth of Q, so we're going to call that 1. That's it. That's all there is to it. That is the implication, right? If it's raining, then the sidewalk is wet, right? That's our implication statement. Let's expand this truth table a little bit. Let's have another statement here, not P or Q. Not 0, doesn't matter what the Q is, because once you have not 0, the first line is going to be 1. Again, it's a not 0, so that line is going to be 1. Not Q, we'll make this to a 0. Or Q is also a 0, so the output is 0. Not Q, that's going to be 0. Not P, that's going to be 0. Or Q, well, Q is 1, and because that's an or, the output to that line is 1. So what do you notice? It's exactly the same. These two statements, P implies Q and not P or Q, are the same. And logically, it kind of makes sense. You could say, it's not raining or the sidewalk is wet, right? That makes some logical sense. But one thing I want to make perfectly clear, it won't always make sense with every English statement. And that's okay, right? That is fine. Really, the reason we learn to translate English statements into these propositional statements is then we can start manipulating things. In fact, one of the most powerful ways to manipulate implication is to change it into the not P or Q, and then we can use all of those theorems and rules that we learned earlier this semester, right? Those become available to you once you change the format, even though we've established these are logically equivalent. They're the same. They just have different forms. All right? Okay. Now we're going to take a look at example 2. And in example 2, we're going to go back to our if it's raining, the sidewalk's wet example, but we're going to put it in terms of set theory. Because remember, everything from propositional logic is directly translatable to set theory. So we're going to say R is the set of all times that it's raining. At the same time, we're going to say W is the set of all times that the sidewalk is wet. once we've put this into kind of a set format, I think it makes more sense to prove this one as a logical diagram, right? As a Venn diagram. Remember, we're saying that R implies W. So when we're looking at a Venn diagram, let's change up colors here. Remember, when we're talking about sets, there's that implied universal set. And if we're talking about time, our universal set is T. T is a set of all times that have ever existed. Within the set of time T is W. W is a set of all times that is a set of all times where the sidewalk is wet. Within that set is R, the set of all times where it's raining. If a time T exists within R, then the time T must exist within W. And that's obvious once you draw the Venn diagram, right? Because R is a subset of W. The times that it is raining is a subset of the times that the sidewalk is wet. Now the sidewalk could be wet if it's not raining, again, if somebody's washing their car or whatever other circumstance. But we know every time it's raining, the sidewalk is wet. It never rains and the sidewalk stays dry. Now, if you could find a time that existed in W but did not exist in R, then you would disprove our implication. Now, when we're dealing with propositional logic, you can't really disprove our implications. They're true because we say they're true. When we get into propositional logic, then we start to prove and disprove these types of statements. But that's what it would take. I would need to find a time inside W that is not also inside R. Okay? So that's translating the same statement we just made using implication and Boolean logic into set theory. All right? Hope that makes sense. If you have any questions, ask in the forum below.